Hello, my name is Lane Geisler, and today we're going to be making our very own artificial blood vessel design. Blood vessels are a series of conduit-like structures that travel throughout the body, carrying important proteins and nutrients to cells and oxygen as well. The blood that travels away from the heart travels through arteries and back to the heart are going to be traveling through veins. When any of these arteries get damaged or veins get damaged, we can bypass or replace the vessel with a transplant. One of the early thinkers in this concept was Mr. Alexis Carrel. In 1912, he actually won a Nobel Peace Prize for his vascular surgery techniques. And he was one of the first to ever create the artificial blood vessels. He actually used rubber, metal tubing, and glass tubing. Throughout the process after Mr. Carroll's studies, we went to synthetic polymers. They became more popular simply because of their properties and biocompatibilities. But none of this could have been possible without Alexis Carrel because he proved that the alien substance being added into the blood circulatory system isn't rejected by the body and it's not going to clot. Current studies on this involve tissue-engineered blood vessels, which are capable of growth and cellular response. So, in order to design our very own blood vessel, we need to get important mechanical and biological details. And so what we're going to be working with is the highest pressure and highest flow of blood in the entire body, and this is the ascending aorta, which comes right out of the heart. Now, I found these dimensions from the National Center of Biotechnology Information, or the NCBI, and they say that the inside diameter of the average adult male is about 29.1 millimeters, and the wall thickness is about 4 millimeters in thickness. The blood flow, the volumetric blood flow is 0.000083 cubic meters per second at about a velocity of 0.64 meters per second. Now, these are all averages on studies that they've done. The average blood pressure, though, is 120 millimeters of hydrogen, which equates to roughly 16,000 pascals. Now, artificial blood vessels can be made from any biocompatible material, and today we're going to be looking at three: polypropylene, tempered glass, and polytetrafluoroethylene. Now that's a mouthful, so we're going to call that PTFE, and you're going to see abbreviations for polypropylene as well as PP. We're going to simulate these three dimensions, or these three materials at three various dimensions shown here. This is given by the project, and this is at 100 millimeters length, 10 millimeters length, and 1 millimeter length. Now, all of the three materials are going to be simulated in these three different lengths, and they're all going to contain the same diameter of the aorta at 29.1 millimeters and a wall thickness of 4 millimeters. So for our mechanical properties, the polypropylene is not a very dense material, but it does have a really high tensile strength and a high yield strength as well, which is good for our study. It's a harder material, but it's also fairly cheap because it is one of the more simple plastics that's used in the industry. Tempered glass, the idea comes from Mr. Alexis and his studies of using glass, but I'm going to use tempered glass because it's a little more hard. The density is a little heavier and it is a little more expensive. However, the tensile strength is very high and the yield strength is going to be high as well, as it's not a very elastic material. Now here we have the PTFE. It also is a pretty dense material, especially for being a polymer. And the price is going to be pretty high. However, we do have a pretty good tensile strength, a fairly low yield strength. However, this is made up with elasticity. Some of that stress is going to turn into the elastic energy and strain. So here's our first 3D simulation. This is of the polypropylene. Up in the upper right-hand corner, you have the stress for the 1 millimeter sample. Now, as you can see, from the arrow at the bottom of the legend there, that we are not close to the yield strength, and the yield strength is where our system is going to fail or yield, go past the elastic region. Luckily, the 10 millimeter and the 100 millimeter show very similar results, and they really do not have that much strain on them, meaning that they're not going to displace too much. You don't have a lot of elasticity. And we do not see that behavior in these glass samples now. These glass samples, again, are not close to the yield strength, but they do not have any elasticity. The strain is very, very low. We're not seeing very much movement whatsoever. However, all 3 samples do not come close to their yield strength, as the yield strength is a lot higher than the polypropylene. In this third simulation here, we have the most displacement, therefore we also have the most strain, and again now the lowest stress. These are all, again, from the standard blood pressure that in the adult human male, right? So we have the most elasticity in the PTFE, the least amount of strain, but again, also we have the smallest yield strength in the PTFE. So here's our stress and strain curves that I made, just so we can look at the graphical model. You can see that the tempered glass does not have any strain to it much, and the more steep the slope of that line is, which the tempered glass is almost straight up and down, and the less elastic that we're going to see. And so in our PP there, this is our polypropylene, we have a little bit of elastic movement. We have some strain going on, but we do see a decrease in the stress, which is good. And keep in mind, we also have a high yield strength there. So our polypropylene is looking promising. But then we have our PTFE that's showing a high strain, which is a lot of elastic movement. We are absorbing a little bit of that from the stress, but our yield stress is so low that we're not going to see very much difference and benefit in it being so elastic. So here we have to make our decision between the 3 materials that are chosen. First off, that we can knock out right away is the tempered glass. Again, it was used in 1912 by Alexis Carrel in the early development of artificial blood vessels. It's a very dense material, and at a high price per weight, the denseness is going to make it to where every unit is going to cost a significant amount of money. A business model just does not agree with that. It's a very hard material, which is good. However, we're going to have weak spots because it's a very complicated manufacturing technique, and it's not very elastic, so it's not going to be forgiving in those weak points or just forgiving under heavy stresses at all. The PTFE we are also going to go ahead and throw out. It is high elasticity, which is good. However, the low stress that it has, the low yield stress that it can take, does not make up for its elasticity because it's not much lower. The stresses are not much lower than polypropylene, and it's displacing a significant amount. Therefore, it's going to rupture earlier than the polypropylene. It also has a high price with its density, so it's going to be a lot more expensive than the polypropylene per unit. And this brings us straight to polypropylene, which we are going to go ahead and use for our artificial design, our artificial blood vessel design. The polypropylene is already used in a lot of mechanical applications, whether it be bone or other grafting techniques and whatnot. It is a relatively hard, a relatively hard material, which takes away from its elasticity, but this allows it to be able to take higher stresses. Therefore, it's not going to yield as easy, and the high yield strength is what puts it above the PTFE. It's a very light material. It's not dense at all. And so the low cost per weight and its light density is going to make it a lot cheaper than the other two options per unit. And it can be 3D printed and very simply manufactured. So here we have the 5 times the average blood pressure, so 5 times 120 millimeter mercury simulation. And again, you can see that this is the worst case scenario, and all three of our yield strengths are not even close to being met with our max stresses throughout the 1 millimeter, the 10 millimeter, and the 100 millimeter samples. So I thank you for taking the time. If you have any questions, you can email me here.